Hi, I'm delighted to be able to join Climate Match Academy to give this keynote talk on future projections of climate. My name's Helene Hewitt. I'm a science fellow at the Met Office Hadley Centre in the UK. In the IPCC Sixth Assessment Report, I was a coordinating lead author, and I co-led the chapter on ocean, cryosphere and sea level change. I'm now the chair or co-chair of the Coupled Model Intercomparison Project, or CMIP. And my background is in ocean, sea ice, and climate modelling. Almost all the figures in this paper can be found in the IPCC reports, so I hope that you'll be able to look them up if you need to. So for the outline of my talk, first of all, I'll talk about IPCC and the Sixth Assessment Report. I'll go on to talk about climate change, what we've observed, what we expect to happen, both from the processes and from what we've seen in paleoclimates. I'll talk about projections of future climate, and then I'll summarise. So first of all, IPCC and the Sixth Assessment Report. So what is the IPCC? Well, IPCC stands for the Intergovernmental Panel on Climate Change. It's the United Nations body which assesses the science related to climate change. IPCC provides policymakers broadly with four things: scientific assessments on climate change, information on the impacts and potential risks of climate change. It lays out the adaptation options, so how we can adapt to what is already changing in the climate system. And finally, it sets out the mitigation options. How can we prevent more changes from happening in the climate system? In the sixth assessment cycle of IPCC, there were 7 reports. First of all, there were 3 special reports, which cut across all 3 working groups. One on global warming of 1.5 degrees, one on climate change and land, one on the ocean and cryosphere in a changing climate. And there were 3 main working group reports: the physical science basis, impacts, adaptation and vulnerability, and mitigation of climate change. And these were then all brought together into a synthesis report, which was released in March 2023. The road to the reports can be long and take many years. So here's an example from the Working Group 1 report on the physical science basis, which I was involved in. So first of all, the outline is scoped. It's drafted, developed by experts who have been nominated by their governments and observer organisations. The panel then approves this outline, and then governments and observer organisations nominate experts as authors. The IPCC Bureau selects the authors, taking into account both the scientific expertise of those people, but also ensuring gender and geographical balance as far as possible. The authors then move on to actually making the assessment. They look at peer-reviewed and internationally available scientific and technical literature, at the data that's out there, some non-peer-reviewed literature produced by relevant institutions as well. They go through a first-order draft, which gets reviewed by experts. Having responded to the comments of those experts, a second draft is produced, which is then reviewed again by experts and now governments as well. This then moves towards a final draft report and a summary for policymakers, or the SPM. These are then sent to governments who review the final draft of the summary for policymakers. With the governments and the authors, there's then a line-by-line approval of the summary for policymakers before the report is then finally published. So not only takes many years, it takes many people. So for the author team, just for the Working Group 1 report, included 234 authors from over 65 countries. 28% of the authors were women and 72% were men. 30% of the authors were new to the IPCC. In the process of making the assessment, the authors assessed over 14,000 scientific publications. They reviewed comments, which amounted to 78,000 comments. and each one is responded to individually by the authors. And finally, 46 countries commented on the final government distribution. Now, the IPCC process is definitely an assessment. So first of all, the authors evaluate the evidence and then look at its agreement. So the evidence can come from observations, from theory, from statistics, from models, from experiments, from process understanding. And then looking at these multiple lines of evidence, the authors can then evaluate its confidence. So if there was low agreement between the lines of evidence, or there was limited evidence, this would lead to low confidence in a statement. If, on the other hand, many of the lines of evidence are in high agreement and the evidence was robust, then this would lead to high confidence in a statement. If we have high or very high confidence in a statement, then the authors can evaluate the statistical likelihood. So if in IPCC we say that it is likely that something will happen, it means there's a greater than 66% chance that that will be the case. Very likely increases that to greater than 90%, extremely likely to greater than 95%, and virtually certain means there's a greater than 99% chance that something is the case. So now I'll talk about climate change, what we've observed and what we expect. So first of all, if we look at this figure, this comes from the frequently asked questions in the observations chapter of the Working Group 1 report. We can see that in the atmosphere, surface temperature has increased. We're also seeing the air temperature in the lowest few kilometers of the atmosphere has warmed. Water vapor in the atmosphere has increased and the atmospheric circulation has changed. In the ocean, the sea surface temperature has warmed. The ocean has taken up more heat. Along with this, the species in the ocean have shifted where they exist. Sea level has risen and the ocean has become more acidic. The ice is seeing many changes. The extent of permafrost is declining. Arctic sea ice cover and snow cover is declining. Ice sheets have lost some of their mass, as have the glaciers. And on land, we're seeing that precipitation has increased. Species are also shifting. The growing season length has increased and the land is becoming greener. So there's many changes across all realms of the climate system. If we look at the temperature change, and here you see it shown in degrees, going back for the last 2,000 years, and you can see that in the recent period, since about 1850, this warming looks unprecedented in 2,000 years. The warming now relative to pre-industrial in the 2011 to 2020 decade shows that the surface temperature has warmed by 1.1 degrees Celsius. And if we look back over this decade, we now see that we're looking at the warmest multi-century period in more than 100,000 years. If we look what's caused the warming in surface temperature, we see that we cannot explain the observed changes by natural causes alone. So that would be changes in the solar or the volcanic forcing that has taken place. It is only when we take into account the human impact on climate through emissions that we can reproduce the observed change in surface temperature. The human influence has caused heating of the climate system. Since at least 1970, there has been a persistent imbalance in the energy flows that has led to excess energy being absorbed by different components of the climate system. In a stable climate, we should see incoming solar energy coming into the climate system and leaving as outgoing energy, and that should be roughly in balance. But in today's system, we are seeing that it is imbalanced. We have the incoming solar energy, but greenhouse gases mean there is less outgoing energy. So the climate system as a whole is gaining heat. Where is that heat going? We've already seen that the atmosphere is warmed, but actually only 1% of that goes into the atmosphere, or it goes into atmospheric warming. Almost all of it goes into warming the ocean. 91% of the excess heat is now in the ocean. 5% of it has warmed the land, 3% of it has contributed to ice melting. So this energy is really accumulating in the ocean. So we see that the planet is warming, and we've seen that 91% of that heat is going into the ocean. If we look back from the data, we can see that in the early period, since the 1970s, most of that appeared to be accumulating in the top 700 meters of the ocean. But as we get closer to present day, we can now see that the heat is going beyond that, and it's going down to 2,000 meters and even deeper into the ocean. We can see that the heat's increasingly going into melting ice and into warming land, and a very small percentage of it goes into heating the atmosphere. So 56% of the heat, over half of the heat, has heated the top 700 meters of the ocean. So we talked about where the warming had come from, and we can see that almost all the observed warming comes from greenhouse gas warming. It's partly masked by aerosol cooling, but human influence is no longer assessed with a confidence level because we are so certain that human influence is the cause. That means that it is taken as a fact according to IPCC. Now let's talk about what we expect to happen in the system. So we know that clouds play a really important role in reflecting radiation back to space. Now, clouds affect and are affected by climate change, but overall, we expect clouds to amplify the future warming. We expect them to become higher, so more outgoing energy will be trapped by clouds. We expect there to be fewer low-level clouds, so that will mean that less incoming energy can be reflected back to space before it reaches the surface of the atmosphere. To counterbalance this slightly, we expect to see more water droplets in the clouds, which would act to reflect more energy back to space. But overall, that's in the balance, we expect clouds to be more amplifying overall. Another part of the climate system which will be affected is the water cycle. So the Earth's water cycle involves evaporation and precipitation at the Earth's surface. As the planet warms, the water cycle is expected to intensify. And this is because the atmosphere can hold about 7% more water vapor for each degree Celsius of global warming. We see this pattern also in the ocean salinity. So the ocean salinity, where it's saline near the surface, reflects the evaporative areas, where it's fresh near the surface, reflects the precipitative areas. And what we're seeing in the ocean is that the fresher areas are getting fresher, so seeing more precipitation. The salty areas are getting saltier, so you're seeing more evaporation. So again, indicating this strengthening of the water cycle. So many people ask, will we see the Gulf Stream shut down? So the Gulf Stream is part of a large vertical ocean current, which is called the Atlantic Meridional Overturning Circulation. The Gulf Stream is part of this system. It's partly driven by winds in a subtropical gyre, but also driven by the sinking at high latitudes. So as the Gulf Stream moves northwards, water and heat are transferred from the tropics to northern latitudes. Close to the poles, the water cools, it becomes heavier, and it sinks to the bottom. And then cold, deep water is exported southwards. In a warmer world, we expect to see the Atlantic meridional circulation to be much weaker. Water near the surface in the poles, we expect to become fresher and warmer, so therefore lighter, and it will sink less. So much less heat and water will be transferred southwards, and the Gulf Stream will weaken in terms of what's driven by the sinking. However, the portion that's controlled by the winds will continue to largely unchanged, but we will expect to see some weakening of this overturning circulation. Another place where we expect to see feedbacks is with the sea ice. So in a warming climate, more sea ice melts in the Arctic in the summer season. We can see that in these figures here. If we look in March, in the early part of the satellite period and the later part of the satellite period, we can see some changes in the extent, but not as much as if we look in September. So if we look in September, in the early part of the satellite period, the central Arctic was mostly covered, even in September. If we look in the more recent part of the satellite record, you can see that large areas of open water remain. This is important because sea ice is effective at reflecting radiation back to space. It has a high albedo. The ocean surface, on the other hand, is much darker and is able, therefore, to absorb much more heat. When we get open water from less ice, the ocean warms and it can melt sea ice from the sides and from below, reducing the ice cover further and giving a feedback in the loss of ice. Now, in the sixth assessment report, we talk about the fast and slow responses, particularly of the cryosphere, to temperature change. So we see that some components of the climate system respond proportionally to temperature change. So, for example, we show here with snow cover. As temperature increases, we expect the snow cover to decline. But if the temperature was reduced, we would expect the snow cover to increase again. This is also true largely of Arctic sea ice. However, other components of the climate system respond much more slowly. So ice sheets is one example of this, also the deep ocean circulation. So in ice sheets, we can see that they might lose mass very quickly and relatively, but it will take a long, long time for that ice to recover. This means that changes to ice sheets and the deep ocean circulation are largely irreversible on human timescales, and we're seeing committed change underway, and this is affecting sea level. So in sea level, we see that global mean sea level has risen faster since 1900 than over any prior century in at least the last 3,000 years. So here we're showing global mean sea level, and you can see going back to 500 years BC that it has now risen very rapidly in the last century. So between 1901 and 2018, global mean sea level increased by approximately 20 centimetres. Not just that, but the rate of global mean sea level rise is also increasing. So between 1901 and 1971, the average rate of sea level rise was about 1.3 millimetres per year. Between 1971 and 2006, that increased to about 1.9 millimetres per year. And between 2006 and 2018, it's increased again to 3.7 millimetres per year. So we're seeing an onward increase of the rate of sea level rise. Human influence has been shown to be very likely the main driver of these increases since at least 1971. In the same way that we looked what was causing heating of the climate system, we can also see what's causing the sea level rise. So if we look, this is one measurement of the sea level rise since 1971 as a time series. If we look at where the contributions for that have come from, we can see that in the early part of the time series, it was largely due to the ocean thermal expansion. So that is, as the ocean becomes warmer, it actually expands its volume. And it was also due to loss of mass from the glaciers. So as ice on land melts, that's like pouring additional water into the ocean, and that also increases sea level. As we've moved closer to present day, we can see that the thermal expansion of the ocean is not just in the top 700 meters, it's also below that, down to 2,000 meters and below. Glaciers have continued to melt, but the contribution of the Greenland and Antarctic ice sheets is increasing dramatically. Their contribution has increased by a factor of 4 between the 1990s and the 2010s. And the contribution of glaciers and ice sheets to global mean sea level rise is now one of the dominant factors. Now, paleoclimates can provide us with analogues for climate states with different carbon dioxide levels. So, for example, if we look at this figure showing the atmospheric carbon dioxide, we can see that if we look at present day, similar carbon dioxide levels existed in the Pliocene, which was 3 million years ago. So although the atmospheric CO2 during the Pliocene was similar, the Pliocene was actually warmer than the present day. This was because the present day hasn't been able to adjust yet to the carbon dioxide levels in the way that it was possible during the mid-Pliocene. Paleoclimate records also tell us about the potential existence of tipping elements in the climate system, such as ice sheets. And past climate states can also be used to test climate models under different forcing conditions. Now, in the mid-Pliocene, of course, carbon dioxide was higher not because of human influence, but they're still useful analogues for us. Now, if we look at the ice sheets, we can see that their extent was very different, particularly in the mid-Pliocene, but also in the last interglacial, another warm period. You can see that particularly in Greenland, the ice sheet cover was much reduced. So at sustained warming levels between 2 and 3 degrees, the IPCC assessed that there is limited evidence that the Greenland and the West Antarctic ice sheet will be lost almost completely and irreversibly over multiple millennia. However, if warming levels were sustained between 3 and 5 degrees C, the sixth assessment report assessed that there would be a near complete loss of the Greenland ice sheet and complete loss of the West Antarctic ice sheet over multiple millennia. So now to move on to projections of future climate. So future climate projections are really complex because of the potential interactions between different parts of the system leading to feedbacks, as I've indicated previously with the cloud feedbacks and the ice albedo feedback. So how do we make quantitative projections of future climate? To do this and to take account of possible uncertainties, we need two things. We need scenarios of future forcing and we need climate models. So first of all, let's talk about the scenarios. So in the IPCC sixth assessment report, we talked about the shared socioeconomic pathways, or SSPs. In the report, we broadly talk about 5 different pathways. We talk about SSP1, which represents a world which is sustainable and looks at 2 different levels of mitigation within that. So we have a very low and a low emissions scenario. The report also looks at SSP2, which is a very middle of the road scenario. It looks at another scenario in SSP3, which represents regional rivalry, and that's a high emission scenario. And finally, we look at a very high emission scenario, which would be indicative of fossil fueled developments continuing apace. There are other scenarios associated with different levels of mitigation, also perhaps introducing inequalities between different countries. These are looked at in other reports, but in the Working Group 1 report, as I say, we look at these very low, low, medium, high, and very high scenarios. The climate models contribute to the Coupled Model Intercomparison Project, or CMIP. For the sixth assessment report, CMIP6 included over 23 model intercomparison projects to look at different aspects of the climate system to help the understanding for the sixth assessment report. Contributions came from 70 different models from modelling centres all around the world. As well as the model intercomparison projects, there is a set of experiments which characterise the models called the DEC experiments, or Diagnostic, Evaluation and Characterisation of Clima. These include long control runs, they include an atmosphere-only run, they include an experiment where carbon dioxide levels are increased to 4 times the current level, and they include an experiment where it's increased at 1% per year. So to extend the CMIP projections beyond 2100, and in some cases to the full range of scenarios, we sometimes have to emulate the model responses. So that is to create very simple versions of the model response that try to capture some of the main features. So if we look at some of the key results from the climate projections, these can be found in the summary for policymakers of the sixth assessment report. We see that if we look in the future emission scenarios out to 2100, and we look at the projected global surface temperature change compared to 1850 to 1900, You see the average result is the bold colour, and then the spread is around that in the shading. So under a very high emission scenario, by 2100, surface temperature could approach 5 degrees Celsius on average. However, if we followed a very low or a low emission scenario, we could start to see surface temperature stabilize or even decline slightly by 2100 and would be able to keep below 2 degrees Celsius. Similarly, with Arctic sea ice, we've seen that that has been declining over the historical period. If we look to the future, we can see that whichever emissions scenario we follow, we're following a very similar path to about 2040. But after 2040, the emission scenarios really matter. So if we follow a very low or a low emission scenario, we'll start to see Arctic sea ice stabilize. However, under the medium, high, or very high emission scenario, we would see a continued decline of Arctic sea ice. And if we cross this dashed line, which shows a practically sea ice free Arctic in September, we see that in all of those three emission scenarios, this is eventually crossed. We can also ask what will happen to sea level rise. So we've seen that sea level rise has risen faster in the recent decades. And if we now look out towards 2100, we see that at 2050, the emission scenario doesn't matter so much. We will see a similar amount of loss from the ice sheets and the glaciers, and a similar amount of thermal expansion occurring, a little bit higher, obviously, in the very high emission scenario. However, by 2100, the emission scenario will matter a lot. So the difference between the very high emission scenario and the low emission scenario can be tens of centimetres of sea level rise difference. So as I've indicated, ice sheets and the deep ocean respond on really long timescales. So whatever happens now, we are committed to sea level rise for centuries to millennia. So we see here this figure which shows the projections for the 5 different emission scenarios for sea level rise to 2100. So in the very high emission scenario, it's approaching a metre by 2100. If we follow a low likelihood, high impact storyline where ice loss is much higher than expected from the Greenland and Antarctic ice sheets, we could see an additional metre of sea level rise by 2100. But sea level rise will continue out to 2300 and beyond. So we looked at the estimates in the 6th assessment report of what sea level rise might be in 2300. So under a low emission scenario, we might be able to maintain global mean sea level rise to 3 metres or less by 2300. However, under very high emission scenario, this could go much higher, approaching 7 metres potentially. And in a case where we had large loss of ice from the Antarctic ice sheet, this could approach 15 metres. These estimates, to go back to look at the paleoclimate proxies, are not inconsistent with what one would expect from a 10,000 year commitment of the ice sheets. So if we look in the last interglacial, which was a warm period, and the mid-Pliocene warm period, we see that a projection of several metres, approaching 10 metres by 2300, would not be inconsistent with what was seen in the last interglacial on very long time scales. So we can, in summary, we have evidence from observations that climate has changed. That's summarised in this figure here. We can understand many of the processes that are involved, even if sometimes it's really difficult to quantify their effects. So to quantify the precise changes in climate and the uncertainties that we will see in the future, scenarios are needed, both of the future climate forcing, and also we need complex climate models. And IPCC really provides that assessment of past and future climate change to allow policymakers to make decisions going into the future. And that just leaves me to thank everybody who's worked on the IPCC reports. And I hope you enjoy the rest of the Climate Match Academy. Thank you.